All right, so in these series of videos for Lecture 2, we're going to continue our discussion of sets, and we're going to get into more operations over sets and ways to think about collections, which will be useful later. All right, so let's go ahead and get started. And just to kind of remind you all of where we're at, we talked about sets in the last set of videos and in class. So we have sets are unique items, and they do not repeat. So we have some examples right here of sets, right? And 1, 2, 3, red and blue, the empty set, the set 5 containing another set 4 and 3 and 8, so on and so forth. We have the inclusive operator. So is something in the set or something not in the set? We have equal operators to say like two sets are equal if they contain the same elements. These two sets are not equal because they do not. And then we have the set builder notation, which allows us to say things like all the elements that some proposition is true. So for example, here is a set that is all the elements between 0 and that aren't great. All the integers that greater than 0 that aren't 15 is kind of interesting set. I don't know why I came up with that one. Here's the cardinality set. Finally, the cardinality set is the number of elements in the set. So I'm missing a line here. I'll try and fix that before I post the slides. But this set is actually of size 2, which is kind of interesting because there's actually 2 elements. There's 1 and then the set 2, 3. So this whole 2, 3 is 1 element in the set. So that's where we get 2. And this set here is actually an infinitely sized set, and I'm also missing my bars, so I'll have to add those in later. Okay, so if a cardinality set is 0, we call that the empty set, but you have to be careful because like this is the set that contains the empty set, and that is size 1. Okay, so hopefully you guys are all caught up. This is what we're going to talk about in the next series of videos, but I'm going to jump in and just talk about subsets now. Okay, so for two sets, A and B, we define a subset written with the kind of this C-like symbol. You see this symbol right here, this C-like symbol right here, as a subset if for all elements of A, then they're also in B. Now, this is something you need to be careful about because, like, remember we defined equality as all the elements of A are in B. And all the elements of B are in A. Now, a subset is only one directional. Equality is kind of like two directional. So when we say that all the elements of A is a subset of B, what we mean to say is that, like, let's say A contains, I have an example on the screen, but like let's do like A contains some set of elements. Right, so we can say these are all the things of A, and then B is either larger, it could be the same, right, or either larger and it's like contained within it, right, is another way to think about it. So if we look through this example, we say 9, 7, 22, every element of A, like 9, 7, and 22 are all in here, so you have 9, 7, 22 right here. And we can say that A is then contained in B, or if you can actually say like A is contained in B going this way, but like the symbol you can think about it as like an alligator, like so this you can see this clearly comes from that symbol here. If you want to think about it that way, it's just like curly. And so but we also have this is notion of subset. Now we have another symbol which is called the proper subset. Written as A also contained in B is a proper subset where A is contained in B, but there's at least one X element of B such that X is not in A. So this example here, like if there was some element, let's say J, since J is not in A, then it's a proper subset. Now, just like in this symbol here, the easy way to think about it is we have A proper subset of B. So this is symbol here. So this is proper subset. Just like with the alligator, right? Remember this symbol here? Just like with the alligator, when you say this, it means it can also be equal. But when you do it without the alligator, maybe I don't know if you guys learned it as an alligator, but I certainly did in school. Without that symbol, it cannot be equal. It's strictly less than. Strictly less than. And never equal. It's like an important equivalency here that you have to keep in mind. So it kind of means the same thing here. So for this one, it could also be the same set. But here can never be double. Let me rewrite this. My logic is all over the place. Let me make this a little bit smoother for you guys. Right. If a I don't know what I'm trying to do here. I'm just trying to say that like it can never be the case that A equals B. I'm just going to write that. Good. Okay, so with that, we have some exercises that I want you to do. And like before in the other videos, I'm going to pause for a second, and maybe I can find some funny hold music on YouTube to play while this is going on. Hold on, I'm just going to pause the video while I find that. All right, I found the perfect hold music. So when I play this, you guys should pause the video or just like think about it. Okay, so we're back. Hopefully you paused during that interlude. By the way, that's a very famous hold music that was in the Cisco system, so you probably heard that on the phone at some point. So let's do these examples. All right, so for the set A, 42, 18, 3, 22, and the set B, 22, 3, 42, 18, is A proper subset of B, or is A just a subset of B? Okay, so remember this symbol underneath. Remember, we just said this a second ago, that these things are very analogous to less than and less than or equal to, right? So if it doesn't have the line underneath, they can't be the same set. Now let's see, are these things the same set? So we have 42, 18, and we have 3, and so I would say, yeah, they're the same set. So it's not a proper subset. So A is not a proper subset of B, but A is contained in B, which is somewhat interesting when you could think about this. So if A is equal to B, then A is contained in B, which is kind of definitionally true, because remember, like just like with the less than or greater than sign, you have this like line underneath that means that. Okay, so let's do the second one. For two sets C and D, where C equals D, is C contained in D? And again, yes, that is the case, because remember, like I said, like this line underneath means that it could also be equal, just like with this less than symbol. And so, yes, it is the case that if C is equal to D, then C is contained in D. Now, let's kind of go a little bit further here. If C equals D, then C is contained in D. That also must mean that D is contained in C as well, right? Because it should work in both directions. Great. And that is actually the last question. So for any two sets E and F, if E is contained in F and F is contained in E, then it must be the case E equals F. Okay, so why do we have to go in both directions, right? So for this one here, let's think about it this way. Now, for this example I just did right here, What I'm saying is I actually start with this understanding that C equals D. So if we know that C equals D, then it must be the case that these two things are equal. Now, for the second one, I'm asking, like, if we knew this, do we know that as well? This is a kind of an interesting if and only if condition. Like, we know we can go one way. We can go from this kind of like understanding to this understanding. Can we go from this understanding back to this understanding? That's kind of the question here. Okay, so let's do this last one here. So what this is saying is that for any two sets, E and F, if E is contained in F and F is contained in E, then it must be the case it equals F. So how could we reason about this? What we're essentially saying is that we have kind of like two pictures here, and you could do a more detailed proof. I actually recorded it, but didn't like it. And you're saying that E looks like this, but also it could look like the following. And since E is both contained in F, and F is also contained in E, that means that all the elements of E are in F, and all the elements of F are in E, right? And that means kind of like that these kind of circles here, they must collapse into each other. And really what we have is that they have to be the same set. Like, that's a really strong reason. Now, you could also reason about, like, if both of these things are true, then there couldn't be any element that isn't in one or the other. But it's actually a pretty straightforward argument just to see that, like, if all the elements of E are in F and all the elements of F are in E, then there is no elements that isn't in both sets. Then they must be equal by the definition of equality. So that's another good one. Okay, I have a couple more examples. Let's do these examples. I'm going to play the hold music. You ready? All right. Hopefully you pause or listen to the whole music and enjoy that. Let's do these last two exercises here. Okay, so the question is the empty set contained in the set 5, 12, 2, and 19? And the answer is, oh, be careful here. It's not a proper subset. It is a proper subset. And the answer is yes. What? Yes, the empty set is contained. Now, here's a kind of an interesting quirk of the empty set. We're asking, all right, so let me just phrase this. What it's saying is, are all the elements of the empty set in, let's call this set A, in A? Well, to reason about that, there are no elements in the empty set. So all of them of which there are none are in A. Okay, let me say that out loud again. So since all the elements in the empty set, of which there are none, so none of the elements, or all the zero numbered elements in the empty set, are in A, thus it must be an empty set. Empty set must be a subset of A, of this set. So the answer is yes. Or put another way, the empty set is a subset of every set. Because it's always going to be the case that none of the elements or all of the non-elements are in that set. So that's kind of a nice corollary that all sets have a subset that is the empty set. Now, this last question is the empty set a subset of itself? Yes, for the same argument. Okay. So that was a lot on subsets, and we're going to move on to the next video where we'll talk about intersection and union.